mode solutions and products and cables and connectors are more expensive than multi-mode because the manufacturing tolerances have to be that much greater. Likewise, another issue is dirt with fiber cables. If you get dirt in them, generally a bad thing. But with multi-mode, there's a greater tolerance for, again, getting that reduced power through, whereas in the single mode system, it can be enough to block all the light. So here we have some just a selection of some different connectors. There's more than this, but you know, one of the most popular ones would be the Neutrik. That's a duocon, which means you've got two fibers. It's very reliable. It's got inbuilt dust caps and protection, but it's also backwards compatible with the duplex LC fiber, which is very handy. And then the other commonly used ones are the SC, which is sort of came around in the beginning of widespread fiber use, but is now not as popular. ST is very popular in the military in the US because it's got the bayonet locking, and then the LC connector is now probably the most widespread because of its use in IT and data centers with SFP modules. So we take a brief moment to talk about the electromagnetic spectrum and the different wavelengths. If we look at the output of the sun, we have a large part of the electromagnetic spectrum, from IR with the larger wavelengths down to UV with the smaller wavelengths. Not all of this is visible to the human eye. Only the sort of visible light part of the spectrum can interact with our eyes. But if we look at the spectrum, we can see that we've actually got a continuous spectrum at various different intensities, but it's a continuous, continuous spectrum. When we look at the same analysis from an RGB display, as we talked about in the very beginning, we don't have a continuous spectrum. We're only using red, green, and blue, and we pulse those different channels in different intensities, and using the makeup of our eye and the fact that we have cells in our eyes sensitive to these specific colors, that's the way that we can recreate all of the different available colors in our vision. But we're not actually outputting the full spectrum of different visible wavelengths. But yeah, we're using the discrete channels. And with our optical devices, most optical devices use wavelengths in the near infrared, and some of these infrared wavelengths, you can still, you know, they're close to visible red, so you can still see some red light coming through it. But typically what will happen is discrete near infrared wavelengths will be used. And here with this OBT device, you can see we've got 4 different channels. In this specific device, these channels effectively act as the 4 TMDS channels. So in this way, we can have the full TMDS signals sent down one fiber. You can multiplex these fibers together, these wavelengths together, using a technology called coarse wavelength division multiplexing. So as an example, here we have 4 different laser diodes, each tuned to a specific wavelength or color. And we take light from these 4 laser diodes, direct them all into the same optical core where they become mixed. All we need to do at the receiving side is separate them from the appropriate photodiodes. So because when you different wavelengths refract different amounts, when you send them through lenses, you come out. So that covers fiber optics. Bill, are there any more questions?
No, there's no questions on the fiber optic part.
Okay, well, let's move on to display. If we have some time at the end, we can run through more of the questions. So DisplayPort came into being in 2008, more or less. this is what the full-size connector looks like. Note the locking springs that are retracted by pushing the button on the connector. So this is one of the big things that people like about DisplayPort. It has a locking connector as standard. DisplayPort came into being for many reasons. A big one was that there's related to being an HDMI adopter and selling their products. Effectively, each connector, I think, is like 50p or 50 cents or something. Which, if you're a graphics card manufacturer and you're putting lots of connectors on your products, that starts to build up. So effectively, a lot of the graphics card manufacturers got together with VESA and came up with their own standard, which was a bit more open. So it didn't sort of require the licensing agreement that HDMI does, but ultimately it does a lot of the same things as HDMI in a more advanced way, but the end result is very similar in terms of getting the primary thing being getting uncompressed video data through a cable and onto a display. So as I mentioned, it's the graphics card manufacturers teamed up with VESA to define the standard. It can use 1, 2, or 4 data pairs, which we'll look at in a minute. It's got a similar 8 to 10-bit encoding that is similar to TMDS. With DisplayPort 1.2, it's up to 21.6 gigabits. Much of the same color spaces supported as HDMI. Likewise with deep color, it supports all HDMI resolutions, and we'll look at how some of the backwards compatibility is designed, and similar 8-channel audio as HDMI 2.0. And you could say HDMI 2.0, DisplayPort 1.2 are somewhat equivalent. They're the closest ones to each other. Now it's DisplayPort 1.4, which is out there. You can buy graphics cards that can do 4, and HDMI 2.1, which is still kind of on paper at the moment. So the key difference between HDMI and DisplayPort is that DisplayPort is using a packet-based architecture, a little bit like HDBaseT. So rather than have channels dedicated to red, green, blue, and clock, a DisplayPort packet will contain all of those components, which gives it some advantages. So DisplayPort has 4 lanes, but those lanes can be deactivated if they aren't required, which reduces the load on your graphics card. So in terms of providing power through a graphics card output, if you can use a lower number of, or if you can give power to a lower number of circuits, a lower number of lanes, even if you're going at a higher speed, having those lanes powered is going to significantly increase the draw through the card, and ultimately you can draw less power through the card. It'll have a longer lifetime, and generally it's nicer for that side of things. So here we have a brief overview of the DisplayPort connector pinout. There's a lot of similarities with HDMI, but instead of TMDS wire pairs, we have the lanes. We have the auxiliary channel, which is a bit like DDC, but it carries a lot more bandwidth and data. We have the hot plug, but we also have another pin for return power, which can be used in junction with this DisplayPort power pin, which is there to provide power for adapters, amplified cables, and similar devices. So you can send a lot more utility power, let's say, through a DisplayPort connection than you can through an HDMI connection. And then we have these config pins, which are important for detecting whether or not an adapter is in place. So for example, if these 2 pins are shorted out, that can be a signal to the source device that a DisplayPort, a passive DisplayPort converter is in place. So what's the difference between an active and a passive converter? Well, if we take an active converter, that will take a DisplayPort port signal in and convert it to